Hello, welcome back to this video. This is 4-4 and we're talking related rates. This is going to be the second video on related rates. In this video, we're going through some examples about how to decode related rates problems as well as set them up and solve them. Alright, we're going to go ahead and dive in, and I'm going to talk about some tips for related rates. When you are working with related rates, the very first thing that you want to do is you want to go ahead and draw a picture of the situation. Pictures are worth 1,000 words. Now, in these pictures, it's important to show movement with arrows and then only label static values, which are constant values, okay? So some ideas of these: a static variable or a static value is something that is constant and something that is not changing, something that is consistent. A dynamic variable, it is changing, something that will be moving, okay? So it's very important to be aware of what's changing and what is not changing. Anything that's moving, you cannot substitute values in right away, and we'll see some of these examples. Step number 2, we want to go ahead, after our picture, we want to go ahead and translate the given information from the problem and label on the paper. And then also translate the question. What do they even want you to find? You need to know what you need to find. Okay? Now a tip. Look at units and be careful when you are decreasing values. Okay? So if it's decreasing, the rate is negative. Number 3, write an appropriate equation to model the situation. And this is very important. Now, I go ahead and I call these first 3 pi. Related rates problems are easy as pi. First, you need a picture. Write down the information that's given, and then you need an equation that ties everything together. Now, in calculus, calculus, as talked up as it is, we really don't have a lot of tricks up our sleeves. You're going to usually do one of 3 things. You're going to differentiate, you'll take a limit, or what we haven't got to yet is integration, but we'll differentiate this equation with respect to time, Step 5, you're going to go ahead, you're going to plug in all known values and solve, okay? So, sometimes when we go to plug stuff in, not all information is given. When this happens, we have to go back. You have to use the original equation to find a missing value, okay? So let's go ahead and let's look at a related rates problem, which is kind of broken down into steps and stages here for us. Example 6. A 12-foot ladder is leaning against a wall, and it begins to slide down the wall at a rate of 2 feet per second. At what rate is the base of the ladder moving away from the wall when it is 5 feet from the wall? Okay, so let's go ahead and let's draw a picture. And I don't get too crazy with my pictures. Wall. There's the wall. Whoop. Floor. Here's the floor. And I'll add some color. Here is ladder. Okay, so I went ahead, I labeled this, and then I have my picture. Now what's happening is this ladder is slipping down. So I'm going to add some arrows to indicate movement. And then when this slips down, the ladder's not going to change. This end of the ladder is going to kick out that direction. Okay, so that's kind of our given situation. I think it's important whenever you're working with a wall and a floor, right? We have a right angle. Okay, so there's my picture in pi, easy as pie. Got the picture? Okay, what's the information that they gave us? Well, they told us that the ladder is 12 feet. Ladder is 12 feet. Okay, well, that's not changing. That is a static value. So I'm going to go ahead and I'm going to plug that in. I know that this is 12 feet, that side. Okay, the ladder begins to slide down the wall at a rate of 2 feet per second. Well, I'm going to need some variables. I'm going to go ahead, I'm going to call this side with the wall x, and I'm going to call this side with the floor y. And what they tell us here is they tell us that how x is changing, dx dt, that distance, x, from the floor up to the top of the ladder, it is sliding down. It's decreasing at a rate of 2 feet per second. So they gave us dx dt. Now they say, here's the question, at what rate is the base of the ladder moving away from the wall? So they want to know what is dy dt, how is that distance from the ladder to the wall changing, that's dy dt, when evaluated when y is equal to 5 feet, okay? So that's our question. Now note, y is not always 5, so I'm not going to plug in 5 into my picture. I have x, I have y, and then this constant value here is 12, okay? So there's all my given information. So pi, easy as pi, e. I need an equation to tie all of this together, all sides of a right triangle. Which one is that? The Pythagorean theorem. X squared plus y squared is equal to z squared, or a squared plus b squared is equal to c squared. In this case, my hypotenuse is 12, so I'm just going to say 12 squared. Okay, there's my equation. All right, there's pi, easy as pie. Now, I'm going to go ahead and differentiate the equation from part C. So the derivative of x squared, 2x times the derivative of x with respect to t, plus 2y times the derivative of y with respect to t, and the derivative of 12 squared is 0. Okay, I went ahead and differentiated with respect to time. Now I'm just going to plug in the information that is given, and this will be very, very simple. You'll see it all kind of come together here. Okay, so 2 times x. I don't have x yet. I'll come back to that. Okay, dx dt, what is that? Well, that is negative 2 feet per second, okay, plus 2y. Well, they want to know what is dy dt when y is equal to 5. So here I'm going to plug in 5 feet, okay, times dy dt. This is what I want to find out. That is what I'm trying to solve. And this is equal to 0. Okay, now I have everything filled in except for the variable I want to solve for, and then my missing variable x. I don't have x. Well, here's where we have to go back, and we're going to have to solve for x. Go back and solve for x. Okay, so when I go back to solve for x, I'm going to use my Pythagorean theorem, okay, right here. So x squared plus, well, at this moment, y squared is 5. This is 5 squared is equal to 12 squared. And I'm going to go ahead and solve this. So x is equal to the square root of 144 minus 25. Okay, and this gives us the square root of 119. Square root of 119. Okay? I'm going to go ahead and I'm just going to leave that. I'm going to leave that value in my equation. I'm not going to alter it at all. Okay? So here we have 2 square root of 119 times negative 2. That gives us negative 4. Negative 4, and that's going to be feet squared per second, plus 10 feet times dy dt. And I need to go ahead and I need to solve. So it looks like I'll add 10 feet dy dt is equal to a positive 4 root 119 feet squared per second. And then I'm going to go ahead and I'm going to divide by 10. Divide by 10. Okay, going up here. and we get dy dt is equal to 4 square root of 119 divided by 10. And I'm dividing by feet, so now my units are feet per second, and we can reduce this. So 2 root 119 over 5 feet per second. And there is your answer. Ta-da! That's it. Awesome. A classic right triangle problem. Expect one of those. Those are extremely, extremely common. Okay, next example. Example 7. They say the area of a circle is increasing at the rate of 5 inches squared per second. Okay, area of a circle is increasing. Sounds like a derivative. Find the rate that the radius of the circle is changing, okay, when area is 36 pi inches squared. Okay, so related rates, easy as pie. I need a picture first. So here is my circle. Such a beautiful circle. Okay, there is my radius. Okay, and so I have a circle that's increasing. So this circle is going to get bigger. It's going to expand. It's going to grow. Okay, so there's my arrows. It's getting bigger. And now I'm going to go ahead. That's P, I. So what's my information that they give us? Well, they said the area is increasing. That's the derivative of area with respect to time is equal to 5 square inches per second. Okay, and they want us to find how is the radius changing. So what's the derivative of radius with respect to time? At the moment, the area is 36 pi inches squared. This is what we want to find. Okay, so there's my information. And now an equation. Well, what ties area and radius together? How about the area formula of a circle? Pi r squared. Awesome. Okay, now I'm going to go ahead. I'm just going to differentiate it. So I'm going to differentiate the equation. So the derivative of area with respect to time, dA dt, is equal to, the derivative of the right side is 2 pi r times the derivative of r with respect to time. And there we have it. There is our equation. Now I just need to go ahead and plug in the information that's given. I know that the area is changing at a rate of 5 square inches per second. I have 2 times pi. What I don't have is r. I don't know what r is. Okay, times dr dt, and that's what they want us to find. I need to go ahead and find this. So I need my radius. I need to know what radius is. So again, I'm going to have to go back to your equation, and sometimes maybe you need a different equation. Maybe they gave me information about a circumference, and I would use that. Here they say the area is 36 pi square inches. Okay, well, if it's equal to pi r squared, can't I divide both sides by pi? Divide by pi. Divide by pi. Okay, so I know that the radius squared is equal to 36 inches squared. Take a square root. Radius is 6 inches. Ta-da! I have it. Now I'm going to go ahead and I'm going to plug this in. So 5 square inches per second is equal to 2 times pi times 6, and that is dr dt. Okay. All right. Simplifying this side, we get 12 pi dr dt, and then I'm going to go ahead and I'm going to divide each side by 12 pi. Divide this by 12 pi, and we get dr dt is equal to 5, and this was inches. So we get 5 over 12 pi inches per second. That's how our radius is changing. Okay, so in these problems, I'm including units. I mean, you don't have to include units, but I mean, including units does not hurt. Does not hurt. Sometimes it can be smart to include them. But sometimes too, you can just figure out what the unit should be based upon the derivative, right? The way radius is changing, well, radius, that's a linear unit, inches per seconds. How is area change? Well, area is in square units, right? Area, inches squared. So relative to time, that's going to be inches squared per second. Okay? All right. I'm going to go ahead. I'm going to pause the video here. I am going to break this up, and I'll do a third video with the next two examples. Give me a thumbs up, like this, subscribe. You can catch the third video on related rates. Catch you in the next one. Peace.